Welcome to this lesson on nanomechanical oscillators. These are among the most sensitive devices ever created, capable of detecting changes down to single molecules and even quantum-level forces. So what exactly are nanomechanical oscillators? These are tiny structures, typically nanoscale beams or membranes, that vibrate at specific resonant frequencies. Imagine a tiny bridge or membrane, just nanometers in size, that can vibrate back and forth. These structures are anchored at their ends and oscillate like a guitar string, but at much higher frequencies. The best analogy is a guitar string. When you pluck a guitar string, it vibrates at a specific frequency determined by its length, tension, and mass. Nanomechanical oscillators work the same way, but they're about 1 billion times smaller. Why build these devices at the nanoscale? There are two critical advantages that make nanoscale ideal for ultra-sensitive detection. First, the effective mass is incredibly small. Because these structures are nanoscale, they can have effective masses in the femtogram to attogram range. That's 10 to the negative 15 to 10 to the negative 18 grams. Second, despite their tiny size, these structures can be very stiff. Materials like silicon nitride or carbon nanotubes provide exceptional stiffness at the nanoscale. Let's talk about the fundamental equation that governs these oscillators. The resonant frequency depends on the stiffness and the effective mass. The resonant frequency, F0, equals 1 over 2 pi times the square root of K over M effective. Here, K is the spring constant or stiffness, and M effective is the effective mass of the oscillator. Notice that higher stiffness K increases the frequency. Stiffer structures vibrate faster. Lower effective mass also increases the frequency. Lighter structures are easier to accelerate, so they oscillate at higher frequencies. Here's an important question. Why does having a very small effective mass make these devices so sensitive? Let me explain. When you add a tiny amount of mass delta M to the oscillator, the frequency shifts. The fractional frequency shift is proportional to delta M divided by M effective. So smaller M effective means larger frequency shifts for the same added mass. The fractional frequency shift, delta F over F0, is approximately negative 1/2 times delta M over M effective. This is the key equation for mass sensing. Let's say the effective mass is 1 picogram, which is 10 to the negative 15 kilograms. If we add a single protein molecule with mass around 100 attograms, that's 10 to the negative 19 kilograms. The ratio delta M over M effective is 10 to the negative 19 divided by 10 to the negative 15, which equals 10 to the negative 4. So the fractional frequency shift is about 5 times 10 to the negative 5, or 50 parts per million. This is easily measurable with modern electronics. This level of sensitivity means we can detect individual molecules landing on the oscillator. This has revolutionized mass spectrometry and biochemical sensing. Let me give you some typical numerical values for real nanomechanical oscillators to make this concrete. The length of these devices is typically 1 to 10 micrometers. That's still small enough to be considered nanoscale in at least one dimension. The thickness is usually 50 to 500 nanometers. This gives them their nanoscale character. Resonant frequencies typically range from 1 megahertz up to 1 gigahertz. Higher frequencies generally mean better time resolution. The quality factor Q can range from 1,000 to 100,000, or even higher in vacuum. Higher Q means sharper resonance peaks and better sensitivity. Let's talk about the quality factor Q, which is crucial for understanding oscillator performance. The quality factor Q equals the resonant frequency, F0, divided by the full width at half maximum delta F of the resonance peak. Q tells you how long the oscillator rings after being excited. High Q means low damping, so the oscillator continues vibrating for many cycles. On a plot of amplitude versus frequency, high Q gives you a very sharp, narrow peak at the resonant frequency. Low Q gives you a broad, flat peak. Sharp peaks are easier to track precisely. Higher Q directly improves your ability to measure small frequency shifts. If Q is 10,000 and F0 is 1 megahertz, you can resolve frequency changes as small as 100 Hz. Besides mass sensing, nanomechanical oscillators are also exquisitely sensitive force sensors. Let's explore how this works. When you apply a tiny force to the oscillator, it causes a static deflection. By measuring this deflection, you can determine the applied force. The force F equals the spring constant K times the deflection delta. This is just Hooke's law applied to our nanomechanical oscillator. Imagine pushing down on the center of the beam with a tiny force. The beam deflects downward by an amount proportional to the force divided by the stiffness. Here's a critical question. What's the minimum force these devices can detect? The answer involves fundamental physics. The minimum detectable force is ultimately limited by thermal noise. Even at room temperature, the oscillator is constantly being kicked by thermal fluctuations from surrounding molecules. The minimum detectable force scales as the square root of 4kBtk divided by q omega 0. Here, kb is Boltzmann's constant, T is temperature, K is stiffness, Q is quality factor, and omega 0 is the angular resonant frequency. Notice that temperature T appears in the numerator. Cooling the device reduces thermal noise and improves force sensitivity. Many ultrasensitive measurements are done at cryogenic temperatures. Let's calculate a realistic force sensitivity for a typical device to see how sensitive these really are. Let's assume a spring constant of 0.1 newtons per meter, quality factor of 10,000, resonant frequency of 1 megahertz, and room temperature of 300 Kelvin. The angular frequency omega 0 is 2 pi times 1 million, which is about 6.28 times 10 to the 6 radians per second. Plugging in the numbers, the minimum detectable force is around 10 to the negative 15 newtons. That's 1 femtonewton. To put this in perspective, 1 femtonewton is about the weight of 1,000 bacteria. These devices can detect forces from single molecules or quantum-level interactions. Now let's discuss some real-world applications where nanomechanical oscillators are making a huge impact. First is mass spectrometry. By measuring the frequency shift when a molecule lands on the oscillator, you can determine its mass with incredible precision. This works even for very large biomolecules like proteins. Second is chemical and biological sensing. You can functionalize the surface with specific receptors. When target molecules bind, the mass changes, shifting the frequency. This enables label-free detection of biomarkers, toxins, or pathogens. Third is atomic force microscopy, or AFM. The cantilever in an AFM is essentially a nanomechanical oscillator. It detects forces between the tip and sample surface, allowing imaging at atomic resolution. Fourth is testing fundamental physics. These oscillators are sensitive enough to probe quantum mechanics at mesoscopic scales, test gravitational theories, and study Casimir forces. When we push sensitivity to the extreme, quantum effects become important. Let's explore how quantum mechanics enters the picture. Even at absolute zero temperature, the oscillator still has zero-point motion due to Heisenberg's uncertainty principle. The position and momentum cannot both be zero simultaneously. The zero-point position uncertainty, delta x zp, equals the square root of h bar over 2 meters effective omega 0. Here h bar is the reduced Planck constant. For a typical nanomechanical oscillator with effective mass around 1 picogram and frequency 1 megahertz, the zero-point motion is on the order of femtometers. This is incredibly small but measurable. Here's a fascinating question. Can we actually measure oscillators so precisely that quantum effects dominate over thermal noise? The answer is yes, especially at very low temperatures. When the thermal energy kBt becomes comparable to the quantum energy h bar omega, quantum effects dominate. The quantum temperature is h bar omega 0 divided by kb. For a 1 megahertz oscillator, this is about 50 microkelvin. At temperatures in the millikelvin range, these oscillators exhibit quantum behavior. Researchers have observed quantum ground states, quantum squeezing, and entanglement in nanomechanical systems. Beyond mass and force, nanomechanical oscillators can sense a wide range of environmental conditions. Let me explain how this works. Temperature affects both the stiffness and the dimensions of the oscillator, causing frequency shifts. By calibrating this relationship, you can use the oscillator as a highly sensitive thermometer. Gas pressure affects the damping and therefore the quality factor Q. In vacuum, Q is very high. As pressure increases, gas molecules collide with the oscillator, reducing Q. This enables ultra-sensitive pressure gauges. Electric fields can induce stress in charged or polarizable materials, shifting the resonant frequency. This makes nanomechanical oscillators useful as electric field sensors. In the presence of a magnetic field, a current-carrying oscillator experiences a Lorentz force that shifts the frequency. This principle enables highly sensitive magnetometry. Let's compare the sensitivity of nanomechanical oscillators to other technologies to appreciate how remarkable they are. For mass sensing, nanomechanical oscillators can detect single large molecules, which is better than conventional mass spectrometry for very high molecular weights. For force sensing, the best devices approach or even reach quantum-limited sensitivity. They can detect forces billions of times smaller than the weight of a single cell. For position measurements, sensitivities at the atometer scale, which is 10 to the negative 18 meters, have been achieved. That's a tiny fraction of the size of an atomic nucleus. Despite their remarkable capabilities, nanomechanical oscillators face practical challenges. Let's discuss the main issues and how researchers address them. First challenge. Fabrication is complex and expensive. Making structures with nanometer precision requires advanced lithography and etching techniques. Solutions include electron beam lithography, focused ion beam milling, and self-assembly techniques. Costs are decreasing as these methods become more standardized. Second challenge. These devices are so sensitive they pick up noise from everything. Vibrations, temperature fluctuations, and electromagnetic interference all affect measurements. Solutions include operating in high vacuum, using vibration-isolated platforms, electromagnetic shielding, and sophisticated noise cancellation algorithms. Third challenge. Reading out such small signals requires extremely sensitive electronics. The signal can be smaller than electronic noise. Solutions include optical readout using lasers, superconducting quantum interference devices for magnetic detection, and lock-in amplifiers for signal extraction from noise. Let's look toward the future and see where nanomechanical oscillator technology is headed. First trend. Integration with quantum systems. Researchers are coupling nanomechanical oscillators to qubits, photons, and other quantum systems to create hybrid quantum devices. Second trend. Massive arrays of oscillators working in parallel. This enables high-throughput sensing and even imaging applications. Third trend. On-chip integration. Combining nanomechanical oscillators with CMOS electronics on a single chip will enable portable, low-cost sensing devices. Fourth trend. Pushing into the regime of macroscopic quantum mechanics. As devices get better, we can test quantum mechanics with larger and larger objects, probing the boundary between quantum and classical worlds. Let me summarize the key equations we've covered that govern nanomechanical oscillators. The resonant frequency depends on stiffness and effective mass. This is the most fundamental equation. The fractional frequency shift for mass sensing. Smaller effective mass gives better sensitivity. The minimum detectable force limited by thermal noise. Higher Q and lower temperature improve sensitivity. The zero-point motion from quantum uncertainty. This sets the ultimate quantum limit on position measurements. Let me leave you with some thoughts on why nanomechanical oscillators matter for science and technology. These devices push measurement sensitivity to fundamental limits set by quantum mechanics and thermodynamics. They represent the pinnacle of precision measurement. They enable entirely new types of science. We can now study single molecules, probe quantum effects in large systems, and detect forces that were previously unmeasurable. They promise revolutionary applications in medicine, environmental monitoring, materials, science, and fundamental physics research. Perhaps most exciting, they bridge the gap between classical and quantum physics, allowing us to test quantum mechanics in regimes never before accessible.